So let's talk about calculating equilibrium concentrations if we have the constant. So how can we do that? There's a method called an icebox, which is the way we're going to calculate equilibrium concentrations. Let's work through an example to see how this works. ICE stands for initial, change, and equilibrium. So if we have a starting point and the reaction is going to proceed either forward or backward, then we can figure out, well, where are the concentrations when we actually reach equilibrium if we know the constant. So let's look at an example with hydrogen iodine gas. Right? So the hydrogen iodine is going to decompose into hydrogen gas and iodine gas. If we started with 4 moles of hydrogen iodide and put that into a container that has been completely evacuated, so it's a vacuum, so there's nothing else in it, and then we put in 4 moles of HI, and it's a 5-liter container. Well, what's the initial situation? And here's our equation. The initial situation is we have 4 moles in 5 liters. Let's make this nice and significant. So that means right now there's a concentration of 0.80 molar of the hydrogen iodide. None of it is broken down yet, so we're starting with 0 for the hydrogen gas and for the iodine gas. Well, how are these going to change? Let's assign a variable. Well, for every time 2 of these go away, 1 of those and 1 of those will happen. So these are going to increase by x, and this is going to go down by 2x. So at equilibrium, we will have 0.80 that's been reduced by whatever 2x is that we've got to solve for. And we will now have x molar of hydrogen gas and x molar of iodine gas. So how are we going to put this all together, making use of the equilibrium constant, which for this reaction is 0.016. Little reminder, K values that are less than 1 tell you that reactants are favored. Only a little bit of this is going to turn into product before it reaches equilibrium. K values that are greater than 1 tell you that products are favored, and the larger it is, the more product is favored. Okay? So the smaller the number is, less than 1, the less of the reactant becomes product before equilibrium. The larger the number is, greater than 1, the more product you're making and the less reactant you're left with at equilibrium. We have this relationship in this icebox, but we have to do some algebra. We have to plug some things in. So remember, the equilibrium expression. So for this reaction, H2, I2, products over reactants, and the reactant raised to its exponent because it's 2HI in the equation. And that is all equal to the equilibrium constant. So using what we just put in our icebox, we said that this is x, and this is 0.8 minus 2x. So let's set that up. X times x, which of course is going to be x squared, and 0.80 minus 2x squared equals 0.016. Well, I'm just going to be clear about my steps here. Well, both of those are squared. This works out nice. If I take the square root of that side and the square root of 0.016, I can make my algebra life a little easier. So, the square root of x squared is x. Square root of 0.80 minus 2x squared is that. And the square root of this, when you pick up your handy dandy calculator and type it in, is 0.126. Now all I have to do is do some algebra. rearrange, distribute, solve for x, it turns out that x is equal to 0.1025. We started off with 2 sig figs, so we'll just call it 0.10. Okay, great. I found x. People have been looking for it forever. Found it. It's right there. I'm not done. If a problem asks for what the equilibrium concentrations are, I have to take x and come back to my ice box and plug it in. So, in plugging it in, this turns into 0.6, and these are 0.10 and 0.10. Remember, these are all concentrations, not individual moles. So that's why sometimes the numbers may not work out, obviously, in terms of mole to mole or gram to gram. But in this space, we have, in this 5 liters, we have the 4 moles. Some of it degrades. So now that we only have 0.6 molar, 0.1 molar, 0.1 molar. So we have to come back and plug it in. So the ice box is a way to organize what do we have to begin with. And it doesn't always mean that we start with all reactant and have no product. Sometimes we have to, if we have, let's just say we didn't have any hydrogen but we had some iodine, the equilibrium concentrations might be a little different. Certainly at the end they would be. Right? So the algebra can get kind of complex here. Here's a little good news. If the K value is low, if only a small amount of reactant turns into product, a lot of times we can ignore the impact of the X, because the answer, if we do it with it and do the algebra out and do a lovely quadratic equation, or if you're really a whiz kid with your graphing calculator, you plug it all in and graph it and find the roots. If you do it that way, or you leave the impact of the X term on your starting concentration out and calculate it without it, and therefore avoid having to do the quadratic equation, if the difference in the answers is less than 5%, because that's considered statistically significant, then you can leave the X out of the your starting term here, your equilibrium for whatever it is that's getting reduced. That usually works with K values that are small, usually smaller than 0.016 though. Things on the order of times 10 to the negative 5 or smaller. A lot of times we see that with weak acids and weak bases, that we can leave out the X term in determining where the equilibrium concentrations are for the reactant, for the thing that's going down. Okay? So, again, initial, change, and equilibrium create an ice box so that you can track how everything changes, so that you get your terms right with your x's. Then write your equilibrium expression, plug in your variable terms where they are, and then do the algebra out and rearrange it. And again, if this term down here becomes a binomial that you have to expand and then use a quadratic equation once you maneuver things around, it gets a little tedious and long. Typically on the AP exam, they wouldn't necessarily have you do all of that mathematical gymnastics. What they're looking for you to see is, do you get the idea? And here's the take home from the general picture. I show you the math to give you an idea. K value is greater than 1. You're going to make a lot of product. K value is less than 1. You're only going to make a little bit of product. And it's always the proportionality. And if you know the K value at a given temperature, given situation, then if you have starting concentrations, you can figure out where the equilibrium is going to land with the one you don't know. So that's using an icebox to solve for equilibrium concentrations.